Okay, so as we said, we're gonna solve the question 4 and 5 for the cohesionless soil conditions. In question 4, we're gonna reanalyze question 1 and 2 by assuming that the free head pile is embedded in a cohesionless soil instead of cohesive soil as with last week. The friction angle is 30 degrees and the unit weight of the new soil is 19 kilonewton per cubic meter. So to solve these questions, if you go back to your lecture notes, to solve these questions, it's similar to these conditions where we have a free head piles in cohesionless soil, and this is the short pile failure scenario, and this is the long pile failure scenario. So we're gonna assume both scenarios. Firstly, we're gonna solve it assuming that we have a short pile failure scenario, and then we're gonna assume that we have long pile failure scenario, and we can check which scenario is working there by checking the value of M maximum, the maximum moments, against the yielding moments on the problem. If we got M maximum is less than My, then we have the short pile failure scenario. If M maximum is more than My, then we have the long pile failure scenario. So we're gonna assume both scenarios here. So if we go to the solutions, as with the last week, we have the diameter, the external diameter of the pile is 305 millimeter, and the shell thickness is 19 millimeter here. So by doing so, we're gonna work out what's the internal diameter of the pile. And after we did that, we need obviously to draw the reactions or the distributions of the force in the problem. As we can see in this figure, we have the ultimate horizontal force on the problem at the head of the pile, and we have the soil reaction here. As we can see here, it's distributed soil reactions, and it's increasing downward at constant rate depending on the unit weight of the soil, because in this problem we have only one soil, and in all these problems in this chapter we assume that we have only one soil, and that soil is homogeneous and with the same properties as well with depth. So the properties will not change with depth, so that will be linear behavior. And then we're gonna assume that the reaction of the soil after this point, after the rotational point, the reaction of the soil is assumed to be F capital, and that's acting at the tip of the pile here. That's by assumption, but in reality, it's a distributed force. It's a distributed force here. Okay, so we need in this problem to find out the amount of ultimate lateral load and the amount of maximum bending moments as well. And we can find as well, if we assume that there is no axial load, we can find the maximum stress developed in the pile as we did with the question 1, but we need now to assume, as we said, the cohesionless soil environments. Okay, so if we go to the solutions, after we analyze the forces on the systems here, okay, we need to find what's the value of H ultimate. So to find the value of H ultimate, we need to take the, as you remember from last week, we have two rules applies here, because the whole problem is under static equilibrium. So we have the sum of the horizontal force on the systems, and we have the sum of the moments on the systems at any point it should equal 0. So we have here about the rotational point and the hinge point should be 0, the moments. So if we take firstly the sum of the horizontal force on the system here, as we can see, we have H capital acting on that direction, and we have the distributed forces here, and we have the amount F. So, and you know, anything after the point F within G, the two reactions here, the reaction of the forces will cancel each other. So that amount will cancel that amount, and the rotational point is here. So if you take within the pile length, which is G, okay, which is this point here, exactly this point here, okay? So the reaction of the soil toward the pile on this directions and on that direction, these two forces will cancel each other. So we're gonna end up with the amount of H here acting on that directions will be equivalent to the amount of distributed forces above the maximum moment points here. So that will be equivalent to the amount of distributed forces within the length F on the system, within the length of the systems. But because here we don't have the value of F, F is unknown and H is unknown, so we cannot benefit too much from the value from the horizontal forces. But we're gonna go back to that later to find the value of F. So it's better to take the sum of moments around the tip of the pile, here, and that will cancel the force, the reaction force F. So we're gonna end up with the amount of distributed forces, okay, and the value of H. If we take the sum of moments around this point, so the moment of H around the tip of the pile will be equivalent to H multiplied by E plus L, and that's minus the value of the moments of the distributed force on the systems, which is equivalent to the amount of equivalent force from that distribution of the forces. So if we go back here, we have already done that here. So that's the ultimate horizontal load multiplied by L plus L, because we took the moment about the tip of the pile, and that will be equivalent to the amount of moments generated due to the distributed force on the system here. So these two values will be equivalent to each other, and we know that the value of E is given, the value of L is given. That's all from question 1, because we're going to use the same values, the same parameters, and the Kp we can find it as well. Kp is equivalent to 1 plus sine phi prime divided by 1 minus c sine phi prime, and we know that the value of phi prime is given on a question 4 as 30 degrees, and that will give us the amount of Kp. The passive reaction, the passive earth pressure coefficients is equivalent to 3 on the systems. So this value is given, so we can find this term here. Gamma is given as 19 kilonewton per cubic meter, and the amount of D is given as 0.305 and L as 6 meter. And E is as 0.5, as we remember from these questions. It's 0.5, the eccentricity on the system. So all the values are given. We can find the value of H by working out the moment about the tip of the pile at the bottom, and that will give us the value of ultimate horizontal load as 288.858. So we work out this value from the principle of static equilibrium on the systems. We have already derived the equation to work out the value of HU directly from the same principle. So if you go back to the lecture notes here, we have already derived this formula. We have already derived these two formulas here. So you can use this formula, as you can see here. You can use this formula directly. It's the same as the one we have derived from the sum of the moments about the tip of the pile. And H ultimate can be found by applying these equations. Or you can as well use this chart to find the value of H ultimate, okay, by working out the value on x-axis of L over D. L is given as 6 meter, D is given as 0.305, so that will be an x-axis. And then you're going to intercept that, the vertical line drawn from the x-axis, intercept that with the curves of eccentricity over diameter value. Eccentricity is given as 0.5 meter, D as 0.305, and that will give you the value of E over D on these curves. If you intersect these two values together, you're going to read the value on the y-axis of H over this term here. And this term here is all the values are given. Kp depends on the friction angle. Friction angle is given as 30 degrees, gamma 90 kilonewton per cubic meter, and D is 0.305. So you can work out this value, the H value, from this chart instead of using this equation as well. So there are three possibilities to solve these questions, either from the static equilibrium principles, or from this equation, which is already based on the static equilibrium principles, or by using this chart, which is already based on this equation here as well. So after we found the value of h, you can as well find the value of moments. You can find it from the derived equations directly. You can use these equations, okay, in your lecture notes. As you can see, all the values on this equation are given in except the value of m maximum. So you can find the value of m maximum by working out the different variables on these equations, okay? So that's from the equation directly, the derived equation, your lecture notes, or you can use this chart as well. It's the same value of L over D and the value of E over D that will give you the value of M maximum over this term, and everything in this term is given as well. So you can work the value of M maximum instead of using the equations. Or you can use as well the principle of static equilibriums. If you continue working with these equations, we know that the value of M maximum, according to this chart here, we got the value of M maximum at this point. So we need to take the value of moments, the sum of moments at this point, and to take the sum of moments at this point, we need to find the value of F or the value of G. So you need to take the sum of moments above this point or the sum of moments below this point, and that will be equivalent to M maximum. But if you take the sum of moments at the upper part and the lower part together, that will cancel the moment at this point, because that will be 0. But you need to hinge this point to make this point as fixed, and to consider only the upper part above this point, above the maximum moment points, or below the maximum moment points. So you can either work out the value of G and the value of F, or you can work out the value of F and the value of H. We have already found the value of H from the previous step. So we need now to find the value of F to work out the sum of moments above the maximum moment points, which is at the depth F. And we can recall that the value of horizontal forces on the system, the sum of the horizontal forces of the system, is equivalent to the amount of distributed force above the maximum moment points. So that's equivalent to the distributed force within the length F. And by doing so, we can find the value of F on the system. We have done that here. So we took the sum of horizontal forces within the line, within the length F, okay, because that's what is equivalent to the sum of the horizontal forces, because below that point, the distributed forces, the reaction from the distributed forces will cancel each other because they're working against each other below this point. So above this point will be equivalent to the H ultimate, and that will be equivalent to this term here. How we work out 52.155, it's from the similarity of these two triangles. We have the big triangles and we have the small triangles here. The big triangles, it's with, this is the base, the base here, okay, of this triangle, big one, and the length is L capital. And we have the small triangle is with this length. So we need to find this value. What's the amount of concentrated force from the distributed force at this point, which is at the depth F within the pi length, and that within the length F, So from the two similarities here, we divide this width by this width, and that width and that the length by that length. So we got this value here as the length of the small triangles here, the width of the small triangle here, of the base of the small triangle, as 52.155 F, and F is the length of this triangle, the small one. And by doing so, we work out these equations, and in this equation, we only have one unknown value, which is F small, the length F is small, because HU we have already got it from the previous step as 288.858 kilonewton. And by doing so, we find the value of F as 3.328. So this is the value of F. So after you find the value of F, you need to take the sum of moments at this point to find the value of M maximum. To find the value of M maximum, we took the sum of the moments above the maximum moment points. So we have this force, the concentrated force H ultimate, and we have the distributed force within the length F, and that's acting at a moment R, which is equivalent to F divided by 3 from the base of maximum moment points. So we have done that here. A maximum would be equivalent to H ultimate, that's multiplied by the moment arm until the point of the maximum moment points, and that's minus half of that's minus the resultant moments from the distributed force within the length F above the maximum moment points. Okay, and we know that because it's a right triangle, so the distributed forces, the equivalence of the distributed forces will act at 1/3 of the right angle from the right angle at the bottom. Okay, by doing so, we can find what's the value of M maximum, because everything on this equation is already known. HU is known, 288.858. Eccentricity is given as 0.5. F is already calculated here in this step. So we can work out what's the value of M maximum on the system, and we got that as 785.346 kilonewton meter. After we find the value of M maximum, you can work out the value of maximum stress. You can find the value of maximum stress developed in the pile, as we have done in question 1. So if you go back to the solution here, if you go back to question 1, you just need to apply this equation here, which is M maximum multiplied by Y value. That's divided by the moment of inertia. This term, the Y value and the moment of inertia, they both independent of the soil type, so they're gonna be the same as the one you calculated in question 1. The only difference is the value of M maximum. So you just need to substitute the one we calculated now from question 4 in these equations, and that will give you the value of maximum stress on the systems. Okay, so the only difference is the value of M maximum. Y will be the same, which is half of the diameter length, half of the pile diameter length, which is 0.305 divided by 2, and the value of the moment of inertia we have already worked out last semester, which is the one here. That's the one. We have already worked out the value of I pile on this equations, and we can see it's only a functions of the pile geometry, which are the pile diameter and the pile shell thickness, the pile external diameter and the pile internal diameter. So you can work out the moment of inertia on the systems, and you can work out from that the value of the maximum stress on the system. So that's for this part of the problem, which is by working out the short pile failure scenario. And then we're gonna assume that the pile failure scenario prevail. Let's go back here to the solution. Okay, so if you continue with the questions, that's question the same as question 2. You need to assume the long pile failure scenario. So for the long pile failure scenario, we need to find what's the value of M maximum. M maximum will be the same as M yield. So M yield is given on the system on these questions is given as 430. So that will be the value of M maximum on the systems, or the M yield on the systems. We need now to work out the value of lateral load carrying capacity of the pile, considering the pile failure scenario, but considering the cohesionless soil as we said before. So considering the cohesionless soil, we have here the distribution or the reaction of the forces. We have two forces on the systems. We have the ultimate horizontal load, which is symbolized as H capital, and we have the reaction of the soil as distributed forces above the value above the plastic hinge point here, because this is the break points or the plastic hinge point, the rotational points. So we have here the distribution of the forces. So we need to work out what's the value of F. F will be different from the one we calculated previously for the short pile failure scenario, because that's depending on the value of the depth of the maximum moment points, and it will be different on both scenarios. So you need to be very careful when considering the value of F from both systems. They are not usable on both scenarios. So you need to work a new F value, and after you work the new F value, you can work the value of H. And as we can see from the sum of the horizontal forces on the systems, we can have one equation, and the sum of moments on the system, we can have the second equation. So first we took the sum of the horizontal forces on the system, that will be equivalent to H, is equivalent to equivalence of the distributed forces here. That will give us equation number 1. Okay. That will give us, as you can see here, this is the sum of the horizontal forces on the system. That's equation number 1. And the sum of moments on the systems, that's at this point. The sum of moments on the system at this point, okay, that will be equivalent to my, and the moment coming from the distributed forces here, and the moment coming from the horizontal forces here. And that will be equation number 2. So we have two equations. We have two equations with two unknown variables, which are F small, the length F, and the amount of the ultimate horizontal load. If we here substitute in this equation 2, if we substitute the value of HU as 26.077 F square, we're going to have one equations with only one variable, which is the length F, and we can work out the value of F by trial and error maybe, or you can work it out using Excel sheet or using your calculator as well. And after you find the value of F in the systems, you can work out the value of HU from equation number 1, which is the sum of the horizontal forces on the systems, would be equivalent to HU equal to 26.077, and the value of F we calculated just here as 3.4 on the systems. Okay, so that's for question number 4, which is the free heat pile failure scenario, assuming the cohesionless soil for both cases, for the short pile failure and the long pile failure. And now we need to reanalyze question 3. Question 3 is different from question 1 and 2 by considering the fixed head pile failure scenario. So it's gonna be different, the solution, because in here we're gonna have 3 different scenarios, failure scenario. We're gonna have a short pile failure scenario, intermediate pile failure scenario, and the long pile failure scenario. And that's obviously different from the one we calculated last semester, because it's gonna be with the sandy soil, with the friction angle. It's a cohesionless soil with a friction angle 30 degrees, the same as question 4, and the unit weight is 19 kilonewton per cubic meter. So if you go to your lecture slides here, as you can see, we have here the free head pile failure scenario for the different cases. For the short pile, you're gonna use these equations here. And these equations, as you can see, it's from the sum of the horizontal force in the systems, from the sum of the horizontal force of the systems, because this is the rotational points, it's fixed from rotation, so it will be displaced as one block here on the system, so we don't have any rotational on the system here. And that will be, and the moment will be concentrated at the top of the pile, at the head of the pile here. So considering the horizontal equilibrium, here we're going to have the horizontal forces is equivalent to the equivalence of the soil reaction here, the disputed force from the soil reactions. You can have these equations to find, and everything in this equation is given. So you can get the value of H ultimate directly from these equations. And to find the value of M maximum, you can take the sum of moments here. You can take the sum of the moments as you can see here, we took the sum of moments at the head of the pile, about the pile head, and that will cancel the value of, and that will cancel the value of h, because h is acting at the head of the pile. There is no eccentricity here because it's fixed pile failure scenario, so we assume no eccentricity. We assume that the h is acting at the ground level, here by assumptions, because it's capped with the pile here, with the capped pile. So by assumptions. To find the moments at the system at this point, we only have the resulted moments from the distributed forces here, because the moment from h, because it's passing through the point, that will be 0. There is no moment arm, it's gonna be 0 here. So that will be equivalent to this value here in maximum, is equivalent to this term, and that will be equivalent to 2/3 of h ultimate multiplied by L, because of the equivalence from the previous equations. You can obviously use these equations, or you can use these two charts as well. This chart to find the value of h, depending on the value of L over D and E over D, and this chart to find the value of M maxima. If you calculate the value of L over D and the value of E over D, you can calculate the value of M maximum by knowing this term as well. So that's for the short pile failure scenario. So if we go back here to the solutions here. Okay. Okay, so for the fixed head pile failure scenario, as you can see, it's the same as the equations I showed you before here. So we need to work out this value from the sum of the horizontal forces on the systems. So H ultimate will be equivalent to this term, and everything in this term is given directly. The value of Kp, we already worked it out as for the 30 degrees. Because it's 1 plus sine phi prime divided by 1 minus sine phi prime. We have already calculated that in the last questions, if you remember. And that will give us the value of the passive earth pressure coefficient, Kp, as 3. The value of gamma is 19 kilonewton per cubic meter. The value of the length of the pile is given as 10 meter. The diameter of the pile is given as 0.4 meter or 40 centimeter. And that will give us the value of H ultimate on the system as 3,420 kilonewton. And then we can find the value of M maximum by taking the sum of moments about the head of the pile, and that will be equivalent to the resulted moments from the distributed forces from the soil reactions on the systems, and that will be equivalent to 22.8 mega Newton dot meter, or 22,800 kilonewton meter. So that's for the short pile failure scenario. For the intermediate pile failure scenario, we can have a maximum. It will be more than in yield. So the yielding moments of the pile material will affect the design of the pile or the failure of the pile, either in intermediate failure scenario or the long pile failure scenario. So in these two cases, we're going to have this condition here. That's for the intermediate pile failure scenario. And as we can see, we have here the My, we have the M maximum value, and we have here the distributions of forces on the systems. We have here until the point of the maximum moment points, and we have here anything after that will cancel each other. That's for the horizontal forces, for the calculation of the horizontal forces on the system. So the horizontal force in the system here will be equivalent to the distributed forces above the maximum moment points, or within the length F on the systems. And that's already, we worked it out here by considering the moments around the pile head. If we take the moments around the pile head, we're gonna have this equation here. And if we put everything back here, My will be given, and all the term in this equation will be given. So you can find the value of H ultimate, and either from these equations or from this chart as well. So you can use this chart obviously to find the value of H ultimate as well. And for the long pile failure scenario, we need to take the sum of the forces between these 2 points, and we can take the sum of moments as well on the systems about the hinge below the pile heads between these 2 points. If we take the moments on the systems at this point, for example, okay, at this point, we're going to have the moment of H about this point will be H multiplied by F, and that's minus My. That's minus the moment of the distributed forces here, and the equivalence of this distributed force from this small triangle will acting at 1/3 of the right triangle, which is 1/3 of the value of F, and that's calculated here, and that will be equivalent to the My here on the other side, here. And as we can see in this equations, so we have, this is equation number 1, and we have another equation from the sum of the horizontal forces of the systems as well. So that will be the sum of forces on the systems. And if we combine both equations, the one coming from the moments about this point, and the one coming from the sum of the forces on the systems, that will give us these equations, and everything in this equation is given, should be given. My, Kp, we can work out from the value of friction angle. The gamma is given, D is given as the pile diameter. So we can work out what's the value of H ultimate on this problem. So if we go back here, this is the value of working out that from the intermediate pile failure scenario. And as we said, we take the moments about this point for the intermediate pile failure scenario. We take it about this point, okay, to find what's the value of My on the systems. And if we take it about this point, we're gonna find HU multiplied by L. That will be M yield plus half of this value here. If we take the moments, at this point, that will cancel the value of F. Okay, so everything here will be, so we take the sum of the horizontal forces in the system here, that will be acting at 1/3 of L, and H multiplied by L, that will give us the moment of H here, and that's plus the value of My, and that will give us the value of HU. And for the long pile failure scenario, we need to take the moments about the second hinge point, and that will give us the value of HU. That's equation number 1, and from the sum of the horizontal forces, we're gonna get another equation. So we have 2 equations, which are F with 2 unknown variables, HU and F, and that will give us the value of HU on the systems by working out first the value of F, then working out the value of HU. Or you can use directly the equations we derived previously on the lecture notes. You can work out with these equations directly to find the value of H ultimate, or you can use this chart as well to find the value of H ultimate for the long pile failure scenario by working out this term on the x-axis and working out this term on the other axis as well as E over D. And that's for the long pile failure scenario. And for the intermediate pile failure scenario, you can use this chart as well to find what's the value of H ultimate by finding the value of L over D on x-axis and the value of My over this term on the curved lines here, on the curved line here. And these are the values of My over this term, 200, 150, 200. If you have the value in between, you need to interpolate between these values, okay? Between these two curves to find what's the appropriate values on the y-axis of this term here to work out the value of H ultimate, okay? So that will conclude this tutorial, okay? I'm gonna upload the video of this tutorial shortly. And if you do have any questions, you're more than welcome to ask now. on the chat. If you have any questions, please ask me.